Okay, so going back to our table, we have covered all of the properties except a couple of ones where we are talking about the property of differentiation and the property of multiplication in the time domain. So maybe it's a good idea. We can take a quick look at the property of differentiation, and we'll also look at that, and then maybe close with looking at one example which is very helpful for us and very instructive also. So we will look at the property of differentiation. Okay, so here is the property of differentiation. The property of differentiation says that if I have a discrete time sequence x of n which has got a discrete time Fourier transform x e of j omega, then the sequence n times x of n. Okay, so basically it's a weighted value of n, weighted by the time coefficient. Okay, the nth sample is weighted by n plus 1 sample by n plus 1. N times x of n has got a discrete time Fourier transform which is given by j d by d omega of x e of j omega. This is the differentiation theorem. Okay, and actually the proof is very simple and direct. So let's write it down. X e of j omega is equal to summation n equal to minus infinity to infinity x of n e power minus j omega n, differentiating the left hand side with respect to omega, x e of j omega is the same as differentiating the right hand side, d by d omega summation n equal to minus infinity to infinity x of n e power minus j omega n. The only term which has got omega is the exponential term. So we can write this as summation n equal to minus infinity to infinity, x of n is just a scale factor, differentiating with respect to omega e power minus j omega n, we get minus j times n. Right? That's the product when you do the power base angle rule. So this is what comes down, and you get e power minus j omega n. Okay, so we will bring minus j outside, summation n equal to minus infinity to infinity. I'm going to combine n x of n, and then I have e power minus j omega. Just one more step, bring this minus j to the other side, x e of j omega. If you bring it over to the other side, what do you get? 1 over minus j is j times d by d omega x e of j omega. This is equal to summation n equal to minus infinity to infinity n times x of n. Think of this as the new sequence e power minus j omega n. So in other words, n times x of n, this sequence has got a discrete time Fourier transform that is given by j times d by d omega of x e of j omega. All right. Now, of course, the last of the examples that I would like to, of the theorems that we would like to do is the multiplication theorem. Okay, the multiplication theorem. So this is the theorem related to multiplication. Okay, the multiplication theorem says if y of n is equal to x of n times, what was the other sequence, what was the notation that was used? X of n times y of n. Okay, we need it to be a product of these two sequences. Okay, so let's call a new sequence w of n is equal to the product of these two sequences, where x of n has got a discrete time Fourier transform given by x e of j omega, and y of n has got a discrete time Fourier transform given by y e of j omega. Okay, so w e of j omega is equal to summation n equal to minus infinity to infinity w n e power minus j omega n, correct? Sorry, y of wn, sorry, wn. Now, this can be written as summation n equal to minus infinity to infinity x of n y of n e power minus j omega n. Now, I am going to relate y of n to y e of j omega. So, this is going to be equal to summation n equal to minus infinity to infinity. The first term is x of n. The second term I am going to write it in terms of the inverse discrete time Fourier transform. Okay, minus pi to pi. I am going to write it as y e of j theta. Again, instead of, to avoid confusion with omega, I am going to write it in terms, because theta is just a variable of integration, e power j theta n d theta. Okay, and of course, there is a e power minus j omega n that is present. Okay. So, now what we would like to do is to look at this expression that we have, interchange the order 1 over 2 pi integral minus pi to pi y e power j theta, okay, and inside you get a summation n equal to minus infinity to infinity x of n e power minus j omega minus theta n. Are you comfortable with that? Basically, I combined the two expressions, and there is a d theta also sitting outside. Okay. Now, this term that is within the summation is the same as x e of j omega shifted by theta. So, this is x e of j omega minus theta. Okay. So, what we get here is 1 over 2 pi integral minus pi to pi y e of j theta x e of j omega minus theta d theta. Okay. Now, this is a form of convolution. This is called periodic convolution, because you are dealing with periodic functions. Periodic functions go from minus infinity to infinity. So, convolution typically will be over the length of the sequence, but here all we are doing is you are going to look at the convolution over one period, and as you shift one of the frequencies, because it is a periodic signal, the next copy will move into position. So, therefore, at all times you will be integrating only from minus pi to pi. Okay. So, just as a visualization, so let us say that you are convolving the following. You are convolving y e of j omega. Let us say y e of j omega has got this spectrum. Okay, from minus pi to pi, and remember, it is a periodic function. So, you will see the periodic repetitions on both sides. Okay. And we will look at another response for x e of j omega. Okay. So, from minus pi to pi, the representation of, okay, so this is, the blue one is y e of j omega. The red one is x e of j omega. Okay. Red one also will be periodic. And on the negative side also you will get a copy of the signal. Okay. So, now of course, what you are doing is time reversing or reversing the flipping it, you will get, and then multiplying it, but remember that your integration period is only between minus pi to pi. whatever falls between minus pi to pi, you will multiply and then integrate it. Okay. Now, if you look at a shifted version of x e of j omega, so basically remember we have to shift the version of it. So, you may get a shift which looks like this. Okay. But there is a next copy which is coming in from the other side. So, now when you do the integration, remember you are still doing between minus pi to pi, you have one portion which is shifted out, but another portion that is coming in because of the circular shift. So, always between the portion minus pi to pi, that is going to be the integration, and this is called periodic convolution. Okay. So, multiplication in the time domain is going to give us a form of convolution which is called periodic convolution, sometimes also referred to as circular convolution, but for now we will use the term periodic convolution. Okay. So, with that we have looked at all of the properties or the theorems that are associated with the discrete time Fourier transform. So, you can, what I would like you to do is to go back home and to study these things in a lot of detail and be able to derive each of these properties very carefully, very thoroughly. Would like you to be able to do that.